Okay, let's unpack this. Welcome to another deep dive. Today, you've brought us a stack of sources pulling back the curtain on two absolutely critical and, well, deeply technical areas of IT, database administration and system and API integration. And you specifically asked us to roll up our sleeves and really lean right into the technical jargon these documents present.
Absolutely. Our mission here is basically to act as your guides through this technical landscape. We're going to navigate the key concepts, the specific terms, the procedures that define these disciplines, extracting the most important technical nuggets based purely on the material you've shared with us.
Right. So think of this less like a lecture and more like a focused technical tour. We're heading into the engine room to understand the components and how they connect, all guided by your material. Let's dive in. We'll start with the role right at the heart of data management, the database administrator, or DBA. Your sources paint a picture of a challenging job, almost expecting DBAs to know everything and, yeah, often demanding long hours. And let's be honest, when something goes wrong in an application, the database environment is frequently the first place everyone points the finger. Your sources even call it guilty until proven innocent.
Yeah, that framing is very real in the IT world. It really highlights the complexity involved.
Yeah.
And the material breaks down the DBA role into specialized areas, which kind of reflects the technical breadth needed. You have application DBAs, right, focused on tuning specific applications. Then there are procedural DBAs who are deep into managing things like stored procedures, triggers, and user-defined functions,
Yep.
UDFs. Then specialists like data modelers, data warehouse administrators, performance analysts, and system DBAs who focus more on the database instance itself and, how it interacts with the OS.
So each specialization demands a pretty different technical skill set then.
Exactly. And these roles touch on precisely the technical areas we need to explore today.
Got it. And one of the most fundamental technical areas a DBA deals with is database design, which starts with the abstract concept of data modeling. Your sources lay out different levels of abstraction here.
They do. You begin with the conceptual data model. This is the highest level, really business-focused. It identifies the major entities. These should ideally be nouns,
Yeah.
right, representing core business concepts and the relationships between them. At this stage, you typically don't name the relationships just to keep it clean.
Yeah.
And it's not concerned with full attribution or normalization yet. It's the big picture view.
Okay, so that's the high-level view. What's the next technical step down?
That brings you to the logical data model. Now, this is a complete detailed blueprint. Entities are fully normalized, meaning you've structured the data according to, well, normalization rules. Every attribute is defined with its specific domain or data type. You specify all candidate keys, identify the primary key, and define all the foreign key relationships between tables.
Right.
You also specify cardinality, like one to many, many to many, and whether relationships are mandatory or optional. This model is a comprehensive technical document, basically ready for physical implementation.
And that leads us directly to the physical database design.
Exactly. This is where you translate that logical model into the actual database structure on a specific DBMS. And a core technical process here is normalization. Your sources specifically mention first normal form, 1NF, which dictates that all underlying domains contain only atomic values.
Okay, atomic value. So what does that technically mean? Is it like each piece of data is a single indivisible unit? Like a cell in a spreadsheet shouldn't contain a comma-separated list?
Precisely, yeah. If a column contains a list or like a group of values, it violates 1NF. The technical problem this solves is that querying, sorting, and manipulating that kind of data becomes incredibly difficult and, frankly, inefficient. In the physical design, you also implement referential constraints. This is where you enforce the foreign key relationships, technically tying the primary key in a parent table to the foreign key in a dependent table.
Okay.
These constraints implement referential integrity rules, defining what the database does when you try to delete a row in the parent table. Your options are technically defined. Restrict, which just voids the delete cascade, which deletes dependent rows automatically, or set null, which sets the foreign key independent rows to null. It's absolutely crucial for maintaining data consistency across related tables.
Right, makes sense. So stepping away from design and into the physical reality, how the database actually lives on storage has significant technical implications. What are some of those considerations mentioned?
Storage is absolutely key to physical performance. Your sources discuss compression, which, well, it trades CPU cycles for reduced I/O because you're essentially reading less data from disk. File placement and allocation are also critical technical decisions. Things like spreading data and index files across different physical disks. That allows the system to read or write in parallel, significantly boosting performance. Separating indexes from data files is a common technique, too, to reduce contention on disk heads.
And what about page size?
Page size is another factor, yeah. Databases read data in chunks called pages. The size of these pages impacts how many rows fit and ultimately how many I/O operations are needed to read a certain amount of data.
And the database system itself manages these pages internally, using different types.
Yes, using different page types. You've got data pages, which hold the actual rows of your tables, and allocation pages, sometimes called space map pages. They track where data is stored and manage free space. These are often organized into larger structures called allocation units. Calculating table size technically involves understanding the average record length, that's the sum of column lengths, plus some technical overhead for each row, and then dividing it by the space available on a page, considering page overhead too.
Okay, let's talk about the technical superheroes of performance indexes. Your sources call them alternate paths to data.
They really are. They are ordered structures, separate from the main data, that allow the DBMS to find rows much faster than reading the entire table. The sources list several types, like unique and non-unique, clustering and non-clustering, which determines if the physical order of data rows actually matches the index order single and multi-column indexes. And they mention underlying technical structures like B-tree, bitmap, and hashing. A critical point, technically, is that the DBMS's relational optimizer is the component that decides whether and which index to use for a specific query. It's not the person writing the SQL.
Ah, okay. So you need to build indexes. The optimizer is smart enough to actually use effectively. What are the key technical reasons for creating an index in the first place?
Well, enforcing uniqueness on primary and candidate keys is a primary one. The index structure technically guarantees no duplicates can exist. Indexes also enable something called index-only access, or covering indexes. This is where all the data a query needs is available directly in the index itself, so you avoid having to access the larger table data at all. Big performance win there. And they also dramatically reduce or even eliminate the need for sorting data for operations involved in things like joins, order by, group by, union, and distinct.
And what's a big technical mistake to avoid when indexing?
Indexing by object instead of by workload. That's a big one mentioned. It means building indexes just because a table exists, or because a column happens to be your primary key, rather than actually analyzing the queries that run against the database. If the optimizer can't find an appropriate index for a query, it resorts to a table scan, meaning it reads every single row in the table. That's a huge performance killer, especially on large tables.
Right. Now, denormalization, that's often seen as breaking the rules of good database design. Is there ever a valid technical reason to do it, according to your sources?
Your sources are very clear on this. There is only one valid technical justification for denormalization, and that is purely to enhance performance for specific critical queries, or maybe to process repeating groups together more efficiently. It's a technical trade-off, really. You gain performance for certain access paths, but you add complexity and potentially introduce data redundancy. That makes updates more complex and increases the risk of inconsistencies. So every single decision to denormalize must be technically documented, explain the reason, and importantly, the steps taken to mitigate those added risks.
Okay, documentation is key there. Speaking of performance, your source defines database performance tuning as, let me get this right, optimization of resource use to increase throughput and minimize contention. Let's break down contention.
Sure. Contention is a technical term simply meaning conflict over a shared resource. In a database context, this often means multiple users or processes trying to access or modify the same data or resource simultaneously. A classic example is two transactions trying to update the exact same row at the same time. One has to wait for the other to release a lock. That's contention.
The sources list quite a few technical causes of poor SQL performance. What are some of the most common culprits you see mentioned?
Yeah, the list is pretty long. It includes those table scans we just talked about, obviously. Also, the lack or improper use of indexes. Using outdated database statistics, the optimizer relies heavily on those stats to make good decisions. Suboptimal table join order. Again, the optimizer makes decisions here too. Using application-side joins instead of letting the database do the more efficient SQL joins is another one. Choosing inefficient join methods like nested loop versus merge scan, depending on data characteristics. Also, inefficient application code that loops around SQL statements instead of processing data in sets. Poorly written subqueries, especially with exists or not exist. And finally, unnecessary sorting caused by operations like distinct, group by, order by, or union. It's a lot, but many boil down to how data is accessed and processed technically.
Right. So to figure out why a query is slow, DBAs need specific technical tools to kind of peek inside the optimizer's brain. What are those tools?
Exactly. The primary tools mentioned are show plan or explain. Show plan typically provides a textual or sometimes graphical representation of the query's execution plan. It shows the optimizer's chosen access path, which tables are accessed in what order, which indexes are used, the join methods selected, and so on. Explain works a bit differently. It writes this access path information to a special database table, often called plantable. The DBA or programmer can then query that table with SQL to analyze the plan details. It's like getting the step-by-step technical instructions the database followed.
Interesting. But tuning isn't just about the SQL itself, though, right? The DBMS itself needs technical attention.
Right, absolutely. Tuning involves configuring the DBMS software itself using installation and configuration parameters. These control things like memory allocation, logging behavior, resource limits, lots of technical knobs. It also means ensuring the DBMS interacts efficiently with other systems, software, the operating system, networking components, middleware, transaction processors. And within the DBMS, tuning memory structures is crucial. The data cache, or buffer pool, is a vital area. It holds copies of frequently accessed data pages in memory to avoid expensive physical disk reads I/O. The procedure cache is another key one. It stores the optimized access paths generated by the optimizer for SQL statements. This allows the database to skip the optimization step and just reuse the plan for subsequent executions of the same SQL.
And the sources emphasize a proactive approach to performance, designing it in early.
Absolutely. Designing performance into applications from the very start of the development lifecycle is technically much more efficient and cheaper than trying to fix performance problems after code is already in production. It's just much harder to re-architect things later on.
Okay, let's shift to availability. It's described as the holy grail for DBAs, especially with, e-business needing databases up 247, 365 days a year. What are the technical foes of availability, according to the sources?
Well, unavailability can stem from a whole range of technical failures. Hardware, obviously server, disk, storage area network or SAN, memory issues, software bugs, both in the OS or the DBMS itself, problems arising from patches or upgrades. Then there's the ever-present risk of human error, actually a major cause. Data corruption, network outages, or even, catastrophic loss of the entire data center. Lots of potential technical failure points.
So what technical strategies do your sources list to counter these threats and boost availability?
Leveraging high availability features built right into the DBMS is a start. Clustering technology is a key technical approach mentioned. This involves linking multiple interconnected servers so they can share storage or distribute workload. This provides failover capability. If one server fails, another can take over its workload pretty seamlessly. Examples mentioned are Oracle RAC and IBM Sysplex with DB2 data sharing. Standby databases, like those supported by Oracle, maintain a transactionally consistent copy of the primary database, basically ready to be promoted if the primary fails. And of course, redundant power supplies, UPS systems to protect against electrical issues.
And NoSQL comes into play here too.
The sources note that for certain applications demanding extreme scalability and availability, particularly with high volume, maybe less structured data carries, those say, their distributed nature and focus on replication often prioritize availability and performance over the strict ACID consistency guarantees you get with traditional relational databases. They often operate on an eventually consistent model, which is a significant technical trade-off you have to understand.
Okay. Now, database change management sounds deceptively simple. Just alter a table, right? But your sources highlight some significant technical complexities and limitations.
Oh yeah, that's a critical point they make. Simple SQL alter statements often cannot perform many common changes easily, or sometimes at all. You frequently cannot, for instance, change a column's data type or length if it involves losing data or complex conversions. You often can't remove columns directly, change partitioning schemes, rearrange column order, or even move a table between different table spaces using just a basic alter statement. The technical limitations are real.
So how are many of these technical changes actually implemented then, if not with alter?
Well, often they require technically dropping and then recreating the database objects. And this leads to a major technical challenge,
Yeah.
the cascading de-drop effect. If you drop something like a table space, it doesn't just disappear quietly. It technically triggers the dropping of everything contained within it. All the tables, all their columns, all keys, all indexes, all triggers, any synonyms or views that refer to those tables,
Right.
and all the associated security permissions and the statistics the optimizer relies on. It all goes.
Wow. That sounds like a potential disaster if you're not extremely careful.
It absolutely is. The system catalog, or data dictionary, contains all that crucial metadata, the technical definitions of the objects, their physical characteristics, security, statistics, everything. But while the metadata is there, the technical process of capturing the original DDL, data definition language statements, needed to recreate the objects exactly as they were, and then reapplying them correctly after the drop. Well, it's complex, it's tedious, and it's highly prone to human error.
And these changes don't just affect the database structure itself, they ripple out, right, to applications.
Yes, definitely. They impact applications significantly. If an application tries to access a database object that has just been dropped and recreated, the DBMS may technically invalidate the program's access path. This often requires technical steps like rebinding the application program to the database, which basically generates a new valid access path. And then imagine propagating complex schema changes across multiple databases, maybe on different servers, possibly in different geographic locations. That introduces significant technical logistical challenges.
Okay, let's move to another core technical duty, backup and recovery. The plan starts with creating consistent copies, image copies.
Right, these are often called image copies.
Mm.
Technical utilities like backup, copy Y, dump, or export are used to create them. A really critical technical detail here, one that's often overlooked by less experienced folks, is ensuring that your data image copies and your index image copies are synchronized. If they represent the database state at slightly different points in time, your indexes won't match your data after recovery, and that leads to severe consistency problems. You have to get them in sync.
Does the DBMS help manage this complex process technically?
Yes, many DBMS, like DB2 for ZOS, which is mentioned in your source, record details about backups, recovery actions, and other system events right in the system catalog and sometimes in specific recovery control structures. This metadata is then used by recovery utilities to figure out exactly which backup copies and which log files are needed for a specific recovery scenario. Utilities can also establish consistency points. For instance, using a command like quiesce to temporarily suspend updates. This ensures you get a clean, transactionally consistent state for your image copy.
The transaction log sounds absolutely fundamental to recovery.
It is the lifeblood of recovery. Seriously. The transaction log, or database log, technically records every single committed SQL change, every insert, update, delete. During recovery, this log allows the DBMS to roll forward, meaning reapply changes made after a backup point, or rollback, meaning undo incomplete or erroneous transactions. Log archiving and ensuring those archives are backed up are non-negotiable technical requirements. And maintaining dual active logging, writing the log to two places simultaneously, provides crucial redundancy against a disk failure taking out your only log copy.
So when a failure actually hits, what's the technical recovery process look like?
Okay, first step is analysis. Analyze the failure type. Was it a media failure like a disk crash, a transaction failure where an application crashed before committing, or maybe an instance failure where the whole DBMS crashed? Then determine the cause and the scope of the damage. After that, you choose the appropriate recovery method. Point-in-time, PIT recovery, is a common technical method described. You restore an older image copy, and then you use the transaction logs to roll forward the database state, replaying transactions up to a specific point in time just before the error or failure occurred. You essentially replay the good stuff and stop before the bad.
And for truly catastrophic events, like losing the whole data center.
Yeah, that requires a proper disaster recovery DR plan. Technically, this involves maintaining backups or maybe replicated data at an offsite location. DR methods can range from restoring full disk volume backups, maybe from tape, to using image copies combined with the DBMS's own recovery utilities, or maybe specialized third-party DR tools. Critically, DR tests aren't just technical exercises. They are crucial for validating the plan, identifying technical weaknesses you didn't anticipate, and ensuring the personnel involved know exactly what technical steps to follow under intense pressure.
Okay. Let's shift gears slightly to technical implementation details for data integrity and security. How does semantic data integrity differ from structural integrity?
Good question. Structural integrity is about the consistency of the database objects themselves, making sure tables, indexes, constraints are all correctly defined and linked up properly. Semantic data integrity, as your sources define it, is about the accuracy and validity of the contents of the data itself. So ensuring data values actually make sense in the business context. Is the salary positive? Is the state code valid? That kind of thing.
Right. And there's often a debate. Enforce this integrity in the application code or in the database itself. What do the sources say?
Your sources weigh in pretty strongly here, stating that using DBMS features like constraints is generally technically superior. Why? Because database-level constraints simply cannot be bypassed by any application program, any user, or any utility trying to access the data directly. Application-level validation, well, it can always be circumvented if someone accesses the data differently.
Makes sense. What are some specific technical integrity constraints provided by DBMSs then?
Well, the primary key constraint technically requires a unique index on the specified columns, enforcing both uniqueness and non-nullability. Check constraints are really powerful. They let you define specific business rules directly in the database using SQL conditions, like Jacobus employee salary is 0, employee salary 100,000 or something similar. And referential integrity, or I constraints, which we touched on earlier, are defined on foreign keys. They technically enforce the relationships between tables, specifying the delete rule we talked about, cascade, restrict, set, null.
What if the built-in constraints aren't flexible enough for a really complex business rule?
Right, sometimes they aren't. If declarative RI constraints aren't sufficient, you turn to triggers. Triggers are essentially event-driven procedural code that's tied to a specific table. They technically execute automatically whenever an insert, update, or delete event occurs on that table. They require writing procedural logic, actual code, to implement custom integrity rules that go beyond what simple checks or standard RI rules can handle.
Temporal tables sound interesting, adding a time dimension to integrity.
They do. Temporal tables technically support tracking data changes over time, maintaining history. The for portion of business time clause, mentioned in the sources, is a specific technical feature that allows complex update operations to correctly span multiple existing time periods in the data. The database system manages the underlying complexity of splitting or merging time intervals automatically, which is pretty neat.
Okay, moving to security. How is authorization technically managed in a database environment?
Database security is heavily focused on managing authorization. That is, controlling who can perform what actions on which specific database objects. DBMSs use technical concepts like roles and groups to simplify the granting of privileges, which are specific permissions like select, insert, update, delete, alter, etc. Understanding the different levels of technical authority, such as SYSADM authority, which often grants near total control over the entire database system, well, understanding that is absolutely critical from a security perspective. Technical security also extends to managing user logins, things like implementing password guidance, technically enforcing complexity rules, locking accounts after repeated failed login attempts, and properly dropping accounts for users who no longer need access. Basic hygiene, but critical.
And a notorious technical vulnerability mentioned is SQL injection.
Absolutely. Your sources flag this one prominently. It's a major risk when applications construct SQL statements using unsanitized user input. The sources point out that using static SQL, where the SQL statement is hard-coded and cannot change at runtime, is generally more secure than dynamic SQL, which is built as a string at runtime and is susceptible if input isn't properly handled. And avoiding hard-coding technical credentials like passwords directly in utility scripts or application code is another fundamental security practice mentioned. Don't do it.
The DBA's technical role also seems to intersect with operating system security.
It does. DBAs often require elevated operating system privileges, maybe root and UNIX, to perform installation, patching, or certain maintenance tasks. This creates a technical security dependency and requires close cooperation with system administrators to ensure privileges are granted only as needed and are carefully monitored, balancing job function with the principle of least privilege.
Finally, compliance mandates like GDPR or IPEA, they introduce specific technical requirements, don't they?
Yeah, compliance requires translating legal and business requirements into concrete technical actions. Each role is to implement the necessary technical controls. This involves technically mapping data elements, identifying which specific pieces of data, like a customer name or health record, fall under which regulations, and then implementing the technical policies and procedures required by those mandates. That could be things like encryption at rest or in transit, fine-grained access controls, and robust audit logging.
Okay, that gives us a really solid technical deep dive into the world of database administration based on your sources. Now let's pivot to the equally demanding technical challenges highlighted in system and API integration.
All right, shifting gears. When you connect systems, you definitely introduce new layers of technical complexity. Your sources highlight some persistent challenges here. Data mapping, transformation, and consistency are huge ones. Dealing with diverse data formats, CSV, Excel, JSON, you name it. Reconciling different technical schemas. And resolving semantic conflicts, where terms like customer technically refer to different concepts or just have different meanings in different systems. That's a significant technical hurdle to overcome consistently.
And security and compliance pop up again in the integration space.
Unsurprisingly, yes. Poorly designed integration architecture can create brand new technical vulnerabilities. Authentication verifying who is making a request, and authorization verifying what that identity is allowed to do failures are incredibly common sources of technical integration issues. Think about debugging HTTP 401 unauthorized errors, or dealing with the technical complexities of OAuth flows, or maybe troubleshooting inconsistent handling of API keys or access tokens, and maintaining compliance technically across multiple integrated systems, each with its own data model and security controls. That's a significant effort.
And scale is always a technical concern, isn't it?
Absolutely. Scalability and flexibility are constant challenges in integration. Traditional methods, maybe relying on older batch processing or custom point-to-point scripts, can quickly buckle under increasing data volumes or transaction rates. Designing integration solutions that can technically scale to handle future load and adapt to changes in source or target systems without requiring a complete re-architecture, that's difficult.
It's fascinating the sources note that people and process issues, like unclear requirements or lack of expertise, often exacerbate these technical problems.
They compound them significantly. If you don't have crystal clear technical requirements for an integration, like how exactly data needs to be mapped or transformed, then implementing it correctly becomes exponentially harder. Similarly, without sufficient technical expertise on the team, designing for scalability or implementing robust security measures just isn't possible.
Troubleshooting these interconnected systems is described as an iterative learning process in the sources.
It really is a continuous technical puzzle. The emphasis on documentation and adjusting processes after resolving an issue is key to building that institutional technical knowledge. A fundamental troubleshooting strategy mentioned is isolation. Techniques like mocking, creating simulated responses from external services, and stubbing replacing dependencies with simpler versions are powerful technical tools for isolating the source of a problem. They let you apply a divide-and-conquer approach, which is essential for managing the complexity.
Okay, so APIs are central to modern integration, but they bring their own specific technical challenges.
They introduce a standardized technical interface, yes, but that interface still has its own complexities. As we mentioned, authentication and authorization failures are frequent technical problems. You'll often see specific HTTP status codes indicating these kinds of issues.
What do those codes tell you technically? Are they standardized signals?
Yes, they are standardized technical signals. HTTP 4XX codes like 400 bad request, 401 unauthorized, 403 forbidden, 401 not found, and 429. Too many requests generally indicate an error originating from the client side. That typically means the request itself was malformed, unauthenticated, unauthorized, targeted a non-existent resource, or maybe the client just sent too many requests too quickly. HTTP 5XX codes, on the other hand, like 500 internal server error or 503 service unavailable signal, an error on the server side. Troubleshooting involves technically checking the API's documentation for specific error code meanings, meticulously validating the structure of your request, headers, body parameters, and using technical tools like Postman or curl to precisely replicate the request and inspect the response details.
API versioning is another technical detail that needs careful handling, right?
Yeah.
Managing changes over time.
Oh, absolutely. It's crucial for managing changes to an API without breaking existing consumers. Your sources mention several technical strategies: URI path versioning, like v1 products, query parameter versioning, like products.version1, and custom header versioning, where you send a specific header, like XAPI version 1.0. Technical best practices involve maintaining backward compatibility for as long as is reasonable, providing crystal clear technical documentation for each version, and having a defined deprecation policy with clear timelines so consumers know when older versions will eventually be removed.
What about API security? What are the common technical methods used there?
Common technical methods include passing API keys, often in request headers, basically to identify the calling application. OAuth 2.0 is a widely used authorization framework. It allows users to grant third-party applications limited access to their data without actually sharing their credentials, using technical concepts like access tokens. JSON Web Tokens, JWTs, are often used as these access tokens, particularly as bearer tokens. Technically, a JWT is a JSON object containing claims pieces of information. It must be digitally signed to ensure its integrity and authenticity. When a server receives a JWT, it must technically validate that signature and also key claims, like the issuer, the intended audience (OD), and the expiration time (expiration).
And there's a specific warning about JWTs.
Yes, a specific technical warning from your sources is that the JWT header's alg parameter, which specifies the signing algorithm, should never be set to none. Setting it to none essentially disables the signature verification, making the token completely insecure. Big no-no. The sources also mention the OWASP PPI Security Top 10, which is a valuable technical guide to common risks. Things like broken object-level authorization, where a user can technically access data they aren't authorized for just by manipulating identifiers in the request, and unrestricted resource consumption, where technical limitations aren't placed on request size or frequency, potentially leading to denial of service. Defense in depth is the core technical principle here. Layering security controls like HTTPS, strict input validation, secure configurations, and rate limiting.
Okay, let's look at troubleshooting data and operational issues within integration. We've discussed the data mapping challenges, but how do you technically ensure data quality during integration?
Right, dealing with diverse formats and those tricky semantic conflicts is hard. Technically, you need proactive data profiling to analyze source data for patterns, anomalies, inconsistencies before and during integration. That's usually followed by data cleansing to actually fix the detected issues. Crucially, you must implement data validation rules, not just in the source and target systems like specific validation rules within Salesforce, as mentioned, but also within the integration layer itself, perhaps as technical checks within your ETL or ELT pipelines to catch problems as data flows through.
Operationally, exponential backoff is mentioned as a technical pattern for retrying failed API calls. How does that work technically?
It's a technical strategy primarily for handling temporary issues like network glitches or transient server load. Instead of immediately hammering a failed request again, you wait for an exponentially increasing amount of time between retries, maybe 1 second, then 2, then 4, and so on. Technical best practices include setting clear limits on the maximum number of retries and the total wait time you're willing to endure. Adding jitter, a small random delay to the wait times, is also important to prevent all clients from retrying simultaneously and just overwhelming the server again. You also need monitoring and logging of these failures. And importantly, you should only retry for specific HTTP error codes, typically 5xx server errors or maybe a 429 too many requests. You wouldn't retry a permanent error like a 404 not found.
Webhooks versus polling seems like another common technical pattern for getting updates between systems. What's the core technical difference there?
Webhooks are event-driven. It's a push model. When a specific event occurs in the source system, it makes an HTTP POST request to a configured webhook URL on the consuming system, sending the relevant data payload. Polling, on the other hand, is request-driven. It's a poll model. The client system repeatedly sends requests to the source system's API endpoint asking, is there anything new? Is there anything new? Technically, webhooks are far more efficient, especially for frequent updates, because data is only sent when an actual event occurs. Polling constantly consumes resources on both sides, even when there are no updates.
So what are the technical mechanics involved in receiving a webhook successfully?
Okay, your server at the designated webhook URL receives an incoming HTTP request, usually a post. You need technical logic to parse the payload, often it's a JSON body. You need to validate the request, maybe using signatures or tokens provided by the source system if available. And the most critical technical requirement, emphasized in the sources, is to send a swift HTTP response, usually just a 200 OK status code, back to the source system as quickly as possible to acknowledge that you received it.
Why the emphasis on the speed of that acknowledgement response?
Because many webhook providers operate on a fire and forget model, or maybe they have very limited retry logic. If they don't receive that fast acknowledgement, the 200 OK within maybe just a few seconds, they assume the delivery failed and might initiate retries. If your processing logic, the part that actually does something with the webhook data, takes a long time and you do it synchronously, right there in the webhook endpoint handler, it will cause timeouts and potentially lead to duplicate webhook deliveries when the provider retries.
So how do you handle that technically?
The recommended technical pattern is to immediately acknowledge the request, send the 200 OK back right away, then place the webhook payload onto a separate message queue like Amazon SQS or RabbitMQ. From there, dedicated worker processes can pick up the messages from the queue and perform the lengthy processing asynchronously, completely separate from the initial webhook request handling. That avoids the timeout issue. It's also worth noting that some providers require a technical handshake or validation process before they'll even activate a webhook subscription. This might involve the provider sending an initial request, maybe an HTTP options request, to your webhook URL. Your server then has to respond with specific technical headers, like webhook allowed origin perhaps, to technically confirm its readiness and consent to receive webhooks from that specific origin.
Are there specific technical security practices recommended for implementing webhook receivers?
Absolutely. Key ones mentioned include always use HTTPS for encrypted transmission. Avoid sending highly sensitive data directly in the webhook payload. Maybe send identifiers instead. requiring the consumer to make a separate, authenticated API callback to retrieve the full sensitive details. Implement secure logging that doesn't expose sensitive information from the payloads. Use technical authentication methods provided by the source system whenever possible, like verifying a signature included in the request headers, validating a shared secret token, using IP whitelisting, or even employing MTLS, mutual TLS, for strong, certificate-based identity verification on both ends. And avoid verbose error messages in your responses that could technically disclose internal system details or vulnerabilities. Debugging the code receiving and processing webhooks naturally requires tools specific to your technology stack, like Xdebug for PHP environments, which was mentioned as an example.
Right. Throughout all these technical challenges, both in databases and integration, having visibility seems paramount. That's where monitoring and logging come in based on your sources.
They are absolutely the eyes and ears of your integrated systems. Continuous monitoring is vital, tracking key API metrics like response time, throughput, request per second, error rate, and overall availability. These can be technically aggregated and segmented by dimensions like the specific API endpoint being called or the client application making the call.
And API logs provide the granular technical detail needed for troubleshooting. What types do the sources mention specifically?
They describe several key types. Access logs, sometimes called request or traffic logs. These capture details of every technical request and its response. Things like the source IP address, the HTTP method used, the endpoint called, the status code returned, and the response time. Error logs are crucial. They document technical exceptions, failures, stack traces, specific error messages, and severity levels. Debug, info, warn, error, fatal. Performance logs track technical timing and resource usage metrics in more detail. And security logs record technical events related to authentication attempts, successful and failed, authorization decisions, and potential security threats detected.
How do you actually make sense of logs when they're potentially scattered across many different integrated systems?
Yeah, that's a huge challenge. Effective log analysis requires specific technical practices. Log centralization is key, aggregating logs from all your different systems, microservices, databases, everything into a single platform. Standardization or normalization is the next step, converting logs from all those diverse formats into a consistent structure so they can be searched and correlated effectively. Crucially, structured logging combined with correlation IDs is a best practice. A unique technical identifier is generated at the start of a transaction or request, and that ID is passed along to every service involved in handling that request. That ID gets included in every single log entry related to that transaction. This allows you to technically trace the path of a request and pinpoint exactly where a failure occurred across multiple services.
Are there specific technical tools mentioned for managing all these logs?
Yes, log management tools are essential for this. Your sources mention tools like Signos, the popular open source ELK stack, which stands for Elasticsearch for search and storage, Logstash for processing, and Kibana for visualization, Graylog, lightweight log collectors like FluentD or FluentBit, and commercial platforms like Splunk.
And finally, APM, application performance monitoring tools, are highlighted as well. How do they fit in?
APM tools provide a broader, often higher-level technical view. They collect telemetry data, things like performance metrics, error rates, resource utilization from across your applications, and the underlying infrastructure they run on. They give you a more holistic view of the health and performance of your entire system landscape. They're really helpful for pinpointing where technical bottlenecks or failures are occurring within your complex integrated environment, often visualizing dependencies and transaction flows.
So, as you can clearly see, the world of database administration and system integration is not just complex, it is deeply intrinsically technical. It demands real fluency in everything from fundamental data modeling concepts like normalization and referential integrity rules to the gritty specifics of indexing strategies and their technical impact on performance. It means understanding performance tuning tools like Explain that literally show you the optimizer's technical plan and navigating the intricate, often risky processes involved in managing schema changes without causing a cascading technical disaster or implementing truly robust disaster recovery plans.
And then, yeah, you connect these systems and you introduce a whole new dimension of technical detail. You absolutely need to understand API protocols, the technical flows of authentication methods like OWIN, how to correctly interpret specific HTTP status codes when things go wrong, You need to grasp the technical mechanics and the performance trade-offs of event-driven webhooks versus request-driven polling, and understand the absolutely critical role of technical practices like structured logging, centralized monitoring, and using tools like APM to actually gain visibility into the interactions between all these moving parts.
It's a landscape defined by specific technical challenges, requiring not just a theoretical knowledge of concepts, but a deep understanding of their technical implementation and, crucially, their implications. This deep dive, strictly based on the sources you provided, has really aimed to peel back some of those layers, highlighting the specific jargon and the key technical points that truly matter in these critical IT fields.
What's fascinating, though, looking at the sheer breadth of technical knowledge we've just skimmed across, spanning database internals, operating systems, networking, middleware, complex integration patterns, security at every layer,
Hmm.
it really raises a question about the individual practitioner, doesn't it?
Yeah, and here's where it gets really interesting, something for you to think about. Considering the immense scope of mastering all these technical domains truly end to end, how much deeper can one single person realistically dive into every single technical aspect before needing to rely heavily on specialized technical tools or automation or just close collaboration with other experts who have even deeper technical expertise in specific niches? It raises an important question. What's the practical limit to achieving true deep technical mastery across this entire ever expanding stack?